ICSE students who send me the questions and they ask me how to do it, and I explain it to them nicely over there. Okay, so we move forward now. We move forward to today's topic, which is 13.2.3, and which is the magnetic field due to a current carrying circular loop. Okay, we had understood in the previous class the magnetic field due to a straight current carrying conductor. Okay, so if I have a conductor in which the current is passing like this, okay, from A to B, what kind of a field am I going to see over here? What kind of a magnetic field am I going to see, and what will be the direction? What is the rule which I can use to find out? We have done all this in the previous class, so just a recapitulation before we go to the magnetic field due to a current carrying circular loop. Quickly, write quickly. Okay, we use the right hand thumb rule, which Snigdha and Siddhant say, and left to right is meaningless over here. Okay, left to right is meaningless, Kushagra. We have to write the right hand thumb rule, okay, which Snigdha or Siddhant and one of them have written. Okay, which means I keep my hand in such a way that my thumb is pointing in the direction of the current. Okay, and I look at my fingers and I see that my fingers are curling in like this. My fingers are curling in like this. Okay, my hand is up over there like this. So I keep and I see that my fingers are curling, which means that I will have oops, what happened? Which means I'll have circular field lines like this. Okay, we know that we get circular field lines with the conductor at its center, concentric field lines, okay, wherein the conductor is at its center. Got it? So that is the first thing. Now, how do I know the direction? I know the direction by the direction in which my fingers curl. Got it? Which means if I am looking from the top, okay, my eye is over here, then to me these field lines are clockwise. These field lines are clockwise because they'll curl in the direction in which my fingers are curling. Am I clear? Yes or no? Many people don't understand this. Even after tens of times they keep on explaining from left to right, from north to south. Okay, these are concentric rings which will either be clockwise or anti-clockwise. Got it? So when I'm looking from the top, when my eye is on top, okay, and I am looking down, then I see them as clockwise because that is the side from where I'm putting my right hand thumb. Okay, so I see that the thumb is pointing downwards and the fingers are curling in a clockwise direction. Everybody understood? So when they ask you such a question, you should tell clockwise or anti-clockwise, and you'll always be looking at your thumb from behind only. So when you're looking at the thumb, how do you see the lines, concentric lines? Okay. Now as we go, we know that the two lines cannot intersect any time, and as we go away from the conductor, the strength of magnetic field keeps on decreasing. Okay, so now we go to a circular loop. Till now we were talking about a straight conductor. Now I bring in a loop, a circular loop. Okay, if I have this circular loop, how are the field lines going to be over here? Okay, and I say that the current is going in from here, okay, and coming out from there. If my current is going from this strand and going out, how can I find out? How can I find out? I again use the right hand thumb rule. Okay, it's very simple. Whenever I have to find the field lines and a conductor is involved, I use the right hand thumb rule. So this time now my thumb is pointing up like that, okay, and my fingers are curling in like this. My fingers are curling in this like this. Okay, this is my arm. So my fingers are curling in like this and my thumb is pointing in that direction. Okay, which means that I am, again I said the lines will always be circular loops. So I get circular loops, I get circular concentric circular loops, and because my fingers are coming out like that, so these field lines also will be coming out like this. They'll be coming out like this. Got it? Now this conductor has numerous points, so each one of those points will make these concentric field lines and all of them will join. Okay, and they to us, if I take one more point this side, okay, so here also I'll have concentric rings. Okay, here also I'll have field lines in the form of concentric rings. Now my thumb over here is pointing down. My thumb is pointing down over here, okay, like this, and my fingers are curling outside like that over there. Okay, so which means that the field lines are coming out. The field lines are coming out this side also. Now most children do this wrong in the examination also, in the board examination also. When I check the board answer sheets, most of the children do this wrong. Okay, they believe that the lines should always be going in one direction. So that side also they take it inside. Okay, but if you see that all the lines are coming out. Okay, I use the right hand thumb rule by the thumb pointing up this side, and now I use the right hand thumb rule with the thumb pointing this side. But what do I see? I see that in both the cases the field lines are coming out. Okay, and in the middle, if you look at the field lines, the circles have become so big that now the field lines are like almost parallel lines. The field lines are almost like parallel lines. Okay, and what do I see? Look, focus on the green arrows. Okay, the green arrows, all of them are coming out. All the green arrows are coming out. Okay, now I take you back to a bar magnet. I take you back to a bar magnet. When we studied the field of a bar magnet, okay, this is north and this is south. What did we see? We saw that the field lines are coming out of the North Pole. Okay, they are coming out of the North Pole and they are going into the South Pole. Okay, we understood that the field lines we always take conventionally to be coming out from the North Pole. Got it? So if I look at this, which means that when I am looking from this side, okay, this face of the loop is behaving like a North Pole. This face of the loop is behaving like a North Pole because all the magnetic field lines are coming out from this side. Now I go to that side and now I look from this side. Okay, and what do I see? I see that all the field lines are going in this side. All the field lines are going in this side. So the other side of the ring is behaving like a South Pole because all the magnetic field lines are going in. Everybody understood? Yes or no? You can't see the diagram? Everybody else can see, beta. All others can see the diagram. I also can see. I am also logged in through a mobile also. So I keep on getting the feedback or whatever is coming on the mobile. We have been telling you need to upgrade your network. Okay, data. Others, are we seeing the diagram? Priya says she cannot see the diagram. The other children, I can see it on my mobile. Others, can you see the diagram? Yes, says Kushwaha, Vanshika Kushwaha. Yes, says Snigdha Siddhant. Yes, says Kushagra. Okay, so Priya, it's the problem is with your network. I've been telling it to you since long. You'll have to upgrade your network. I can't help it in help in any way in that. Okay. So everybody understood now? Okay. I'll just quickly read out from the book to ensure that I didn't miss out on anything. We have understood the patterns. Okay, done. Suppose this straight conductor is bent in the form of a circular loop and a current is passed through it. How would the magnetic lines look? We have seen that the magnetic field produced by current carrying conductor depends inversely on the distance from it. We know this, we studied this. As we move away from the conductor, the magnetic field will become weaker and weaker. So it's inversely proportional to the distance. Okay. Similarly, at every point of a current carrying circular loop, the concentric circles represent the magnetic field lines. That also we know that the some children had written left to right, and I said that doesn't make any difference. Okay, that doesn't make any sense. When I'm talking about the field lines, I have to talk only in terms of concentric circular loops. Okay, I cannot say left to right, top to bottom, straight lines. I cannot talk in terms of straight lines. Magnetic field will always be in circular loops. So it the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. By the time we reach at the center of the circular loop, the arcs on the wire carrying current would give the arcs of these big circles would appear to be straight lines. And there you have. I'll change the color just so that you can focus on that. Okay, here as we move to the center, they look like straight lines. The circles have become so big that now they look like straight lines which are parallel to each other. Okay, so every point on the wire carrying current should give rise to magnetic field. We have taken just 2 points over here and I have shown you these points. Okay, there are numerous points and each point of the wire will make such concentric rings. At present I have picked up just 2 points to make you understand. Now every point in the wire will make these magnetic field lines. Okay, and they because of these, now these two have made 2 lines in the middle. Now there are numerous, so all those lines will make straight lines in the middle. So in the middle I will have many lines which are parallel to each other. Okay, and they are close by together. So last time we had understood that if the lines are very close by, then the field is supposed to be very strong. And number 2, if the lines are parallel, then it shows that the field is uniform. Okay, so by applying the right hand rule, it is easy to check that every section of the wire contributes in the magnetic field lines in the same direction. I have checked it for 2 points. You can check it for any other point and you will always see that towards the left of the screen, okay, these field lines will appear to be coming, and when I go behind to the right of the screen, then to me the field lines will appear to be going in whichever point I take on the circular loop. Okay, so the magnetic field produced by a current carrying wire at a given point depends directly on the current. I increase the current and what do I see? I see that now the rings have gone to a little greater distance and the distance between these magnetic field lines now decreases, showing that the field has become stronger. So if I increase the number of the amount of current, the field becomes strong. This is a question which CBSE asks you. Okay, they ask you how can you increase the magnetic field due to a current carrying loop. So the first way you can do it is by increasing the current. You increase the current and the magnetic field also goes up. Okay, the second method, now this field is produced by only one circular loop. Okay, so suppose I bring in many circular loops. Okay, so the field because of each circular loop will now add up. Okay, and my field will become n times the magnetic field which was being produced by one loop. Got it? So my magnetic field now will become n times. So I can, the other way of increasing the magnetic field is by increasing the number of loops. Everybody understood? Yes or no? Sir, please scroll down a bit. Okay. What do you want to see? What do you want to see? Okay now? Okay, so now we do activity 13.6. If you have understood, give me a yes and I take you on to activity 13.6. Okay, Priya says she has understood. She gives me a yes. Others, have you understood? Anything you want to discuss, you please discuss it. Snigdha Siddhant also give me 3 thumbs ups. Okay, which means both of them and somebody else also sitting with them has understood. Otherwise the thumbs up should have been 2 in number. Okay, chalo, we move forward. So now my kids have understood this, so I move on. Okay, we go to activity 13.6. Now what I do is I take a cardboard. This is a cardboard. Okay, I make in 2 holes in it. I make in 2 holes in it. And now I bring in a copper wire. Okay, I bring in a copper wire and I bring it from below the cardboard, and now I make a loop out of it. Okay, and I take it back down. Okay, I make many loops. Okay, I turn it a few times. I turn it a few times so that it is not a single wire now, and it is comprised of quite a few loops. Okay, now what I do is I sprinkle some iron filings, the small pieces which you file iron and then they come out. I put some iron filings on this cardboard. Okay, next what I do is I connect this to a battery. Okay, I connect this to a battery, and then I connect it to a plug-in key. I connect it to a plug-in key. I plug in the key, okay, and then using my finger I start tapping this cardboard. Tuck, 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 tuck. Okay, and what do I see? I see that now these iron filings, they are arranging themselves in concentric circles. Okay, the iron filings, they are arranging themselves in concentric circles, the same way like we had done in the previous one. Okay, so now around the loop they arrange themselves in concentric circles. Okay, and the more the number of loops, the greater is the distance up to which iron filings arrange, and lesser is the distance between concentric layers being formed by the iron filings. Are we understanding, everybody? Yes or no? I'll bring it to the center. Okay. So everybody understood activity 13.6. This is find out the magnetic field produced by a current carrying circular coil. It's a coil. Okay, it's not a loop. You can see I have made many yellow wires, so it's a coil. Okay. Okay, so both of you are laughing now, so I get 2 laughing faces, laughing smileys. Okay, now I go to something which is known as solenoid. Okay, now what is a solenoid? Now if I have a insulated copper wire, I'll change the color. I want copper to look like copper. Okay, I pick up this color. So now if I have many circular loops of an insulated copper wire, okay, wrapped closely, and you can see it looks like a cylinder, isn't it? Wrapped closely such that it looks like a cylinder. Okay, and one more thing, that its length is greater than its diameter. Okay, its length is much greater than its diameter. Then such a roll, a circular, such a circular coil is known as a solenoid, which is known as a solenoid. Okay, so two things. The first thing, they said that it is insulated copper wire. So somebody will have to tell me, why insulated copper wire? Why do we use insulated copper wire? Now, why not anything else? And if I use copper wire, then why do I insulate it? Quickly. Tell me, why do we use insulated copper wire? Waiting for your answer. Okay, because if we use without insulation, current flows in the shortest path. Very nice. And they get short circuited so that it cannot behave as an electromagnet. Okay, and now Snigdha Siddhant have written, I don't know whether it is Snigdha or whether it is Siddhant, whosoever out of the two siblings, out of the two twins has written, but he has given me the correct answer. Okay, now suppose this was not insulated, I wrap it up. Okay, I wrap it up like this very closely. Okay, then my current is not going to go in loops. Okay, suppose the current is coming from here, then the current straight away passes to the next circular loop and it moves out, which means I wanted it to go in circles like this, but it is not going in circles. It is simply passing straight because each circle is touching the other one and there is no insulation. Okay, so I use an insulated copper wire because I don't want it to go straight. I don't want it to take the shortest route and go straight. I want it to go in circles. So if it is insulated, then even if they are touching, it will not go to the next loop. It will only flow through the conductor and go in circular form. Okay, number two, I am using copper because copper has very less resistivity. Okay, so the heat which is going to be produced is going to be very less. Okay, it being a good conductor of electricity. Okay, everybody understood? And I want current to flow because I will get a magnetic field only when current flows through it. If I take some substance which has got very high resistivity, very high resistance, then no current is going to flow through it and my purpose will be defeated. Everybody understood? Yes, no? Okay, we now go to finding out how does the magnetic field pattern look like. Okay, so what do I do is I again take a cardboard. And this time I make holes in it which are parallel to each other. I make holes like this which are parallel to each other. Okay, and now I do the same thing what I had done in the previous one. I pick up a wire from down, I insert it and I bring it over here. Okay, and then I take it and I bring it from the next one, again insert it and bring it in the next one, again insert it, bring it in the next one and next one, and finally I pull it out. Okay, so I have made 5 circular loops in the cardboard. Okay, and now I bring in a battery. Okay, I bring in a plug-in key. I haven't plugged the key closed at present, it's still open, so no current is flowing. Okay, So now I bring in the next thing which I was using previously also. Those are the iron filings. Okay, why the iron filings not coming? So I put in the iron filings haphazardly. I just sprinkle them using a pepper sprinkler or a salt sprinkler. I've sprinkled them. Okay, and now I plug in the key. Now I plug in the key and current starts flowing, and I tap it. I tap it again gently with my finger so that they arrange. Okay, and what do I see? Now I see that I have field lines which are coming out like this. I have field lines coming out like this. Okay, and on the other side I have field lines going in like this. The iron filings arrange themselves like this. If I look at the middle, I see that the iron filings have arranged themselves in straight parallel lines like this. Okay, so does this remind you of something which you have earlier studied? Do the pattern of these field lines remind you of everything which you have studied earlier? Tell me quickly. Do these lines remind you of something which you have studied earlier in class 8 or in my previous class? In the previous class also we had discussed this. No? Nobody's replying? Magnetic field lines of a bar magnet, Priya says, and she is correct. Okay, Snigdha Siddhant says just magnetic field lines. So magnetic field lines of what? And Priya gives us the answer. Okay, Kushagra also says magnetic field lines. Magnetic field lines of what? They remind us of the magnetic field lines of a bar magnet. Okay, if you remember, we had done the same activity using the bar magnet, and we had seen that the iron filings had arranged at the poles. Okay, like this, at the poles. Okay, and beside they were like this, circular loops running from the north to the south. We took a needle and we had plotted them, and then also while plotting with a needle we had found out that the magnetic field lines are starting, they are coming out, emerging out of the north pole and not intersecting, without intersecting, they go into the south pole like this. So these also look similar. Okay, now if I plot the field lines using a solenoid, okay, if I plot the field lines using a solenoid same way on the cardboard, okay, then to me the field lines appear as though they are running, just a minute, okay, to me the field lines appear as though they are running from one side of the solenoid to the other like this in concentric rings. Inside the solenoid you can see that they are parallel to each other. Okay, so I have field lines which look like concentric rings and they are parallel inside the solenoid, and they seem to be emerging from one side and they seem to be going into the other side. So these field lines look exactly like a bar magnet. Okay, now since they seem to be emerging out from this side, okay, so this side of the solenoid behaves like the north pole and that side of the solenoid behaves like the south pole. Okay, and inside if you look again, you see that the field lines are equally placed. Okay, equally placed. The distance between them, here you can see the distance is quite a bit. Okay, where I'm marking with green, here you can see the distance is quite a bit, but in the middle the distance is very small, extremely small. So the lines being close by suggests that the magnetic field inside, number one, is strong and they are parallel lines. So number two, I get to know that the field inside a solenoid, the magnetic field inside a solenoid is uniform. Everybody understood? The magnetic field inside a solenoid is uniform and it is very strong. correct? Hey, we need to adjust the screen. You're sleeping. You know what? See, I have to move it this side. The children also are asking me to scroll. It is going out of the screen. Now it is going out of the screen. So I need to, not here. I need to go there. Just a minute, I'll show you. Configuration, over here. Over here, the screen is not in place. Yeah, it's not in place, not in proportion. Fit to screen. Now perfect. Now it is correct. Now it is perfect. Thank you. Now I hope you can see the screen properly. Huh? I just figured out what problem you are facing. Okay. So the learning out of this is that a cylindrical solenoid behaves like a bar magnet. The magnetic field that it produces is similar to a bar magnet. Okay, so one side of the solenoid behaves like north pole and the other side of the solenoid behaves like a south pole. Okay, inside the solenoid the magnetic field lines are straight and parallel, showing that the magnetic field inside the solenoid is uniform and strong. Okay, if I insert a soft iron, okay, a cylindrical soft iron piece, which color I'll pick up blue. Okay, so if I insert a cylindrical piece inside a soft blue, this thing is soft iron cylinder inside it. So what does this blue soft iron piece? It gets magnetized. Okay, and such a magnet is known as a electromagnet, which we'll study in the next class. Okay, such a magnet is known as a electromagnet. Because of the magnetic field produced by the solenoid, this soft iron gets magnetized. Why do we use soft iron? Why don't we use iron or steel or anything else? We use soft iron because soft iron has very poor retentivity. Okay, which means as soon as I switch off the current, it will stop behaving like a magnet. Okay, it will stop behaving like a magnet. Everybody, what is it, Vanshika? What? Thanks, guy. What are you writing over here? Okay, now I give you a question and let me see whether you are able to figure out or not. Okay, now you have to focus and see how I am making the solenoid, and you have to tell me that which side of this solenoid is going to work as behave as a north pole, and which one is going to behave like a south pole. You have to try it and then I will give you the answer. Okay, so now this is positive, this is negative, which means the current is flowing up like that and coming back like that. Okay, and what else? I name it. This is A and this is B. So you have to tell me out of A and B, which is going to behave like the north pole and which is going to behave like the south pole, and you have to give me a valid reason also. This is just a teaser, then I'll tell you how to find out. Priya says that A is north, okay, which means that B is going to be south. Others, Snigdha Siddhant say that they speak what Priya spoke, the absolutely reverse of that. They say that A is south and B is north. Others got two opinions, two different opinions. One says A is north and the other set says that A is south. Don't worry, just you have to write A is north or south. You can take either one of the two things. If you have a justification, very nice. Okay, very nice. Snigdha Siddhant do a lot of studies. They have studied, they found the reason also. They're telling me the reason also. Okay, no more answers coming. Kushagra says A is South Pole. Okay, so we have 3 votes, Snigdha, Siddhant and Kushagra, for A as South Pole, and only 1 for North Pole as Priya. Okay, so now what is the how do we find out? I simply look at this. Okay, so I make a loop like this. Okay, and I can see that the current is going up on that side of the loop and it is coming down on this side of the loop. Okay, up on this side of the loop and down on this side of the loop, which means that the current is going in a clockwise direction. Okay, which means that the current is going in a clockwise direction. Now if I place my thumb over here, okay, if I place my thumb over here and I curl in my fingers, okay, I curl in my fingers, so the thumb is up and the fingers are curling in like this, the fingers are curling in like this. Okay, which means the magnetic field lines are in the direction of the fingers, so which means my magnetic field lines are going in. You can see that they are going in. Yes or no? Correct? They are going in. Okay, and we know that if the magnetic field lines are going in, it is a south pole. Okay, so you have to remember that if the direction of current is clockwise, it has to be south pole. It has to be south pole. And now I was looking from this side. Okay, my eye was over here and I was looking that side. Now my eyes goes the other side and now I am looking this side. Now if I look at the circular loop, okay, from that side, then what do I see? I see that the current is, if I am looking from that side, okay, so I turn it like this, and this is my view. Now my eye is over here and I'm watching it. Okay, so what do I see? I see that the current is climbing up this side and going down this side. Okay, the current is climbing up that side and it is going down this side. Got it? So what do I see? This is anti-clockwise. Okay, so if it is anti-clockwise, then it will behave like a north pole. You can remember that? Okay, so we'll give you some more questions of this type in the next class, and you can tell me how is the coil or the solenoid going to behave. You have to remember that if on looking from that side you see the current going anti-clockwise, it will behave like a north, and if it is clockwise, it will behave like a south pole. Okay, that's all for today's class. I hope you enjoyed it. Okay, and please go through this in the next class. When I come, then we will go to the experiment, wherein you current carrying conductor, experiences of force when placed in a magnetic field. We'll do that activity and then we go into finding out how a motor can be made. Right? That's all for the day. Thank you very much. Bye bye. See you.